All right, so I'm going to get started just by running the different configurations of my program. First, I'll do program 1, which is determined by this define. Let's see here. I'll clear my terminal. There we go. So it'll print out the program steps here and be really verbose because it logs all of the writes. And the blue LED, which is flashing. That just goes indefinitely. I have the PNG of the scope output on the in the repo. So now I can do. This will do the status version. I have a debug and a status build, and the status one just has less verbose logging, so that might be useful to show. Yep. And so it really just talked about initializing the thing, and then it doesn't print out when it's doing all the reads. But yeah, so that's that portion. So I'll go back to debug. And switch to program 2. Oh, there. Okay, so this is also going to be pretty verbose, but I guess it does the 5 runs, so I'll just let it do those, and then I'll do the less verbose version. Yeah, while this is going, I'll show you the 2 error conditions I check for that I set the LED red. One is during the DSP callback, I think. Is it? No, it's, yeah, during the DMA callback, if there's not enough space to create the DSP callback, then I set the LED to red. And the other one is if the sign has bad values, I'll set the LED to red. So yeah, I guess that was the verbose version. Exited the app after 5 runs. Then I'll go over the output on the less verbose version just because I don't think we really need to see all of these reading and writing statements. Okay, so it created the sign table, initialized DMA, and created the timers. Did 1 run, printed out all of the DSP information and the timestamps for the last DMA start to finish. I did another run. It turns off the LED 0.5 seconds after it was requested. Trying to get through the timestamps here. So it was turned on at 25.9 and then turned off. Oh, geez, it's hard to. I'll see it at the last one here. So turned off at 33.0, was turned on at 32.4. Is that right? Yeah, that's right. So the blue LED is being turned off and on independently of the DMA transfer, I guess was my point. So that was the 4 modes. It does maximum, minimum, average, standard deviation. All right, so let's see. I'll show you the lookup table code. That's in this sign module. I took this sine wave function from the white book, generated it into a lookup table, and then when you want to get the samples, you just do this function that has side effects and just gives you the next sample and rolls over. The mod is expensive. That was one thing I did not optimize away. I didn't find a need. Let's see. Oh, it looks like I'm just using this standard sine. I guess I didn't even use the one from the white book, but it works. Let's see, so that's the sine generation. And I can show you the DAC ADC module here. So there's a function to write to the DAC and read from the ADC, and I just use polling to read rather than an interrupt. And let's see what else we got here. Oh yeah, so all the free RTOS tasks are in one module, and so for program 1, it only creates the writing timer, which is a free RTOS timer that just writes to the DAC every 0.1 seconds, which is 100 milliseconds here. For program 1, it's a blue LED. For program 2, it's the green LED. And I did the extra credit portion where I used the semaphores for program 2 to make sure that when this blue LED is set here, there's a semaphore taken and it's not released until this timer callback, which is up here somewhere. This ended up being a big file. Yeah, so this timer gets called, and then we release the mutex. Okay, what am I missing? So I have the periodic 0.1 second task that I showed. There's another task for program 2, which is this write ADC task. And that's the one, or read ADC task, where it just pushes the ADC value onto a circular buffer, the ADC buffer, and then when that is full, then we initiate the DMA transfer and do all this logging and such. And we get the timestamp via this helper function that gives you a struct with various portions of the timestamp string. That's how we use them later. Let's see, so then the DMA transfer happens. I can show you that code. One thing I did that was not in the assignment, I tried to use the interrupt for the DMA transfer, but I couldn't get it to fire. So I ended up just doing polling. So you pass in a callback to the DMA transfer function from tasks and then calls your callback at the end rather than in an interrupt, which was kind of unfortunate, but that's how the callback back in tasks gets called, which copies the ADC buffer to the DSP buffer, not the actual samples, but the read and write pointers and all the bookkeeping stuff, and then it resets the ADC buffer. And then it creates a task to do the DSP stuff. And that's where all this math is. And that's, I think, the next task, this one, that gets all those values, calculates them here, and then reports them all here. It saves the timestamp from the last DMA start and finish. And then after 5 runs, it stops the other timers, and then the task is deleted every time. So at run 5, all the timers are stopped, and the program effectively stops. And again, ADC values from the scope are in the repo. So I think that is everything. Let me know if I missed anything. Thanks.